All right, so just picking up on where we left off, we'll talk about graph algorithms, and one of the most interesting and common graph algorithm is finding the shortest path between points. So, and this is commonly used on like GPS systems that you probably all have on your phone. So the idea is if we had a graph, and the edges between the graphs may or may not have an orientation to them. So an orientation is a direction of heading. You can go from this node to this node, but you can't go from this node back to this node because there's an arrow here. So that would be kind of like a one-way street. And if there were arrows in both directions, that's kind of like a two-way street, but then we could just get rid of the arrows. So no arrows implies a two-way street. Okay, so if we wanted to go from, so the nodes here are represented as numbers, and if we wanted to go from this node to, let's say, our final destination of this node. So our goal is to try to figure out what's the quickest way to get there. So you might think the idea would be to say, leaving this node, it would take one hop to get to this node and 5 hops to get to this node. So the quickest way to get from here to here would be 1, and the quickest way to get from here to here would be 5. But can anyone make an argument why that may not be true out of those two choices? So if I was to make the statement, the quickest way to get from here to here, since these are the only ways you can get in one hop, from this node to this node, this 1 would have to be the quickest way. And to get from this node to this node, this 5 would have to be the quickest way. Is there anything I said that, out of those two statements, anything that is true and maybe something that's not true? Okay, so yeah, so an important part of understanding this algorithm is the statement, so this is now assuming all of these edges are positive, all edges are positive numbers. This would not be true if they were negative numbers. But if they're positive numbers, then it is true the quickest way to get from this node to this node is taking this path of 1. But the statement, the quickest way to get from this node to this node takes this path of 5 may or may not be true. Because we could go from this node to this node at a cost of 1, and then find some other way to get here at a cost less than now 5 minus 4. If I could get there in less than 4, that would be a better. So one thing is for sure, the quickest way to get from this node to this node is 1. But the statement, the quickest way to get from this node to this node is 5, that statement may or may not be true. So the way this algorithm works, it says only record stuff that's definitely true. Don't record stuff that maybe is true. So we look at all the ways out of this node, we have a 1 and a 5. I'm sorry, a 1 and a 5. So we say, well, this is guaranteed to be the quickest way to get there. So what we're doing is we're recording at each node how far away, as best we know, it takes to get from the original node to that node. So we know at the first pass, we know we can, the time it takes to get from this node to itself is 0. The time it would take to get from this node to this node is 5. The time it would take to get from this node to this node is 1. And all the other nodes we have no direct way to get to so far. So the first thing we're going to do is we're going to add, once we conclude that this is the best way to get to this node, we're going to add that to our answer. So we're going to build an answer tree. Okay, so we know after one pass, we know that getting from this node to this node, this is the best way to get there. Okay, now, given this as our answer, what is the quickest way to get to any of the other nodes? So now what we want to do is we want to update. Now that we've added this node to our answer tree, we want to say what's the quickest way, does that help us get to any other node? And by adding this node, we can now get to this node in 3 hops by taking this 1 plus this 2. So this node went from being infinitely away to 3 units away. This node, which was a 5, didn't get any better because we can't go through here and then go directly up here. There's an arrow pointing down here, but you can't really see it. So adding this node to our tree improved this one. Doesn't connect to this one or this one, so it doesn't help these get better, and didn't help this one get better than the 5 we already know. Okay, so now on the next pass, we now have this and this in our answer. Now we say out of all the nodes we can reach, what is the one we can get to the quickest? And it turns out we can get from these two to this one and this one. This one and 3, this one and 5. So we've convinced ourselves that getting here in 3 cannot be better. There's no way to get a better answer than that. We may be able to go to here in 3 and then get to here in less than 5, so we're not going to declare this the right answer, but this will now be the best answer. The best way to get to this node is to go from here to here. So now this becomes part of our answer. So what this is saying so far is, starting at this node, the best way to get to this node is a path of 1. That's for sure. There'll never be a better answer. The best way to get from this node to this node is to go 1, 2 for a total cost of 3. There'll never be a better answer. We also know that we can go from, this used to be a 5, now we could go 1 plus 2 plus 1 and get here in 4. But that may not be the best answer. Maybe we can get to there, or like if there was another road for a half, we might be able to do better than the 4. So out of all the things, so the way this works is you start off with a tree of just your source node, and you just keep, at each pass, you keep adding one more node once you convince yourself you know the quickest way to get to that node. Then with that node being added, you then say, out of all the other ones I could get to, what's the absolute best, which node has the absolute best way to get there. Okay, so once we say we know these 3, then we ask ourselves, what's the best way to get to any nodes we can get to? Well, we know we can get to here in a path of 6, and we know we can get to here in a path of 4. So that means we know for sure the best way to get to this one is to take this path. And we can't say the best way to get to here is 6 because there may be, maybe if we went through this one of 4, there might be a quicker way to get to here. So we add this path to our answer. So now our answer becomes like this. So the first 4 nodes, we have now found out the best way to get to those, nodes. And by adding this 4th one, does that help us get to anything quicker than what we knew before? And the answer is yes. We used to have no way to get to this node. Now we know how to get there in 8. 1, 2, 3, and then plus 4 more. Gets us there in 8. And also going 1, 2, we used to know how to get to this node in 6 by going 1, 2, 1 plus 2 plus 3. Now that we added this node to our answer, we can get to this node by going 1 plus 2 plus 1 plus 1. We can get here in 5, and that's a better answer. So it's a good thing we didn't color this in and say, oh, I know the quickest way to get there, because we found an even quicker one. So now that this has been added to our answer, we ask ourselves, what's the quickest way to get to anything we can get to? Well, we can get to here in 8, and we can get to here in 5. So we know for sure the best way to get to this one is this path. This may not be the best way because we may be able to get to this 5 and then come in another one. So we add this one to our answer. So that would be this path gets added to our answer. And the best way to get to here is in 5. Now at this point, if our original question was, how long does it take to get from here to here, we're done. But if we want to just be complete, we can say, okay, what's the best way to get to this node? And the choices are 4 plus 4 or 5 plus 1. Which of those two is a lower number? And then we'll say, okay, the best way to get here is in 6, and the path would be from here to here, to here, to here, to here. So now we've answered, what's the quickest way to get from this node to every node? But if you're looking from one node to a particular node, as soon as you finally add it to your answer key, you can stop. You can stop the route. Okay, so just talking, looking at what is the algorithm for the code we just did. The algorithm would go, we would initially have to, we'll do an initial pass, we'll take all our vertices, we'll say that every vertex is initially infinitely away from the source, the one we're starting from. And we'll also, just for bookkeeping reasons, we'll keep a list of who the parent is in case once we finally find out what is the quickest path, we might want to say, how do you get there? So the pi vector, which is the parent of V, will help us go, you hop from here to here to here, so on. Okay, and then the source, the original one, we say that one is 0 away from itself. So it initially starts off, the source node is 0, you travel 0 to get there because you're already there. And everything else is infinity away. And then what we're going to do is every time we add a new vertex to our answer, we're going to say, does that make any other ones even better? So basically we're going to repeatedly add a vertex, then ask ourselves, does that make any other path better? If so, make it better, and then add another one, and so on. So we're going to have this routine called relax. I think a better name, or it might have been reduce, but the authors of our textbook called it relax. And what you basically do is you say, given 3 vertices, you ask yourself, is the way I know how to get there right now, is that the best way? Or would going through another vertex and then 2 would be an improvement? And if it's an improvement, so that the distance to V is greater than the distance to some point U and then the cost of U to V, then let's go to U and then go from U to V and make that the next, now the best way to get there. So does that make sense what this relax thing is? Because this relax subroutine is going to show up in another algorithm too, so we want to make sure we understand this. So this would be like, for example, if you're saying, at the point where we said, I know how to get to here in six hops. I know how to get to here in 6 hops. But then we added this node to our graph, and we said, okay, I'm going to compare 6 to going to this vertex, going here, which costs 4. I'm going to compare 6 to 4 plus 1. And whichever of those 2 is less, I'm going to go with that answer. So I'm going to look at every vertex. So in other words, if this value had a 6 on it, like it is over here, and I call the relax routine saying, I have a choice. I can stay with 6, or I can now say, go to this one, and then add 1 more, and ask which is lower. And if going to this node and then 1 more is lower, then I'm going to go with that instead of my current value of 6. Okay? So that's what the relax routine is doing. So it's basically saying is your best answer that you know of, can it be made better? So I'm asking is, if the distance that I know of right now, the best answer I know so far, if that's worse, if that's bigger than, worse than, going to this new node and then going from the new node back to where I'm trying to get to. If this gives me a better answer, then I'm going to copy that one over. Then the distance becomes these 2. The smaller of the 2 gets copied over. And then I'm going to say that the parent of the vertex I'm looking at, the node right before it would be this one. So I'm keeping track of the path. So then this is a subroutine. This is where we initialize how far everything is away from the source. This is a subroutine that's going to be used every time we visit a node and say, oh, I know a better way to get there. I'm going to record the better way. They call it relax, but like I say, they should have called it reduce or better path. So anyway, they called it relax. And then Dijkstra gets credit for the shortest path algorithm, so it's called Dijkstra's shortest path algorithm. And you take a graph. The graph has weights and an initial source. So we initialize, we call everything, every node of the graph is infinitely away except for the source, which is 0 away. And then we start putting all the vertices into some data structure Q. And while there's some data structure Q, we always extract the one out of all the choices of all the nodes we could eventually get to. We take the one that is closest to our tree so far. Take that one, add it to our answer set, and then we say for every vertex that one touches, relax them. See if that helped us get a better answer. So let me just show you again from the picture. What we're basically doing, like, let's say at any one of these steps, if let's say so far our answer was this node, and this node, we know the fastest ways, starting here, to get to each of these two. The other three we're not sure of. So we say to ourselves that of all the things that of all the vertices that these are connected to, we want to pull out the one that has the smallest distance of all of these that we know of. So our nominees were 3 plus 1 is 4. We have no way of getting here, so this was still at infinity. And 1 plus 2 plus 3 getting here in 6. So out of this choice, and this choice, this was the best one. So we have to have a data structure to store these in and be able to say, give me the minimum one. So maybe a heap would be a good data structure for that. We pull out the one with the lowest value out of 4, infinity, and 6. We pull out the one with the lowest value. We add that to the answer. Update all these values, and then do it again. So that's what that last step is. So the last step on Dijkstra's algorithm is we're basically saying we have this data structure, we put every vertex in it, and as long as it's not empty, we pull out the minimum one, add that to our answer set, and then we say for every vertex connected to the one we just pulled out, see if it makes anything better. Call relax and say, instead of going directly to U, can I go from U, instead of going from S to U, could we go from S to V and V to U? Would that be an improvement? And if it's an improvement, we'll record the improvement. Okay, so any question about the algorithm? So it's basically, we're going through the picture and then looking at the code that would walk us through the picture. Okay, so now we want to look at the running time of the algorithm. And so the first step, initializing every vertex to say you're either 0 away from, you're the source, so you're 0 away from yourself, or you're infinity away from yourself, would take, we would actually keep that in an array, so that's not part of our picture. So that would take time proportional to the number of vertices. The time it takes to run the relax step, so what does the relax step do? It compares one number to the sum of two other numbers, and if the sum is smaller, it copies the sum over. So that's a constant time operation. But this may get called many times, but the relax step runs constant time operation. Okay, so the part of the algorithm that says, let's pull a vertex out of our data structure, the one that's the smallest one, and then ask, of all the things you're connected to, let's call relax. Okay, so the while loop on line 5, maybe we should put the code back up. The while loop on line 5 runs v times, so that the total running time of line 6 is v squared. But let me put that code back up. Okay, so this while loop runs 5 times. Runs V times. So this thing, which is going to keep extracting the smallest one out, if we had a two-dimensional array, this routine would run V squared times. Copying the answer over would be a one-time operation, and then calling relax on everything you connected to would get called also V times. So we want to choose a good data structure to make the running time better. So the total running time of lines 8 and 9, where we're calling relax, is going to get called every time there's an edge we're connected to, if we use adjacency list. Since the total number of vertices of the whole adjacency list is 2 times E. So if we used an array of adjacency lists, then the number of times line 8 and line 9 would run would be 2 times 1 for every edge in the graph. So that would be proportional to E. So the 3 separate parts of Dijkstra's algorithm, part 1 runs order V, where we initialize everything. The second part would run V squared, and the third part would run 2 times E, which is proportional to E. And then we make an observation that since V squared is always greater than V, we don't really need to keep this around. So this is, again, the big O notation. Remember, as V and E gets very, very large, one of these components is going to dominate all the time of your algorithm. Well, without a doubt, this part will dominate this part because it's V squared. So we really don't even have to record that. Saying that this algorithm runs V squared, that's a big statement. That means it's a time-consuming algorithm. And then the last part is proportional to E, but since V squared will always be, this is kind of just remember from the graph theory, V squared will always be bigger than E, because even in the worst case, where every vertex is connected to every other vertex, the number of edges in the graph, the maximum number would be V times 1 minus V, if everything's connected. And you know, a map of a country like the United States, yeah, every city is connected, so that would be the worst case scenario. So what we're basically saying is the running time of all the steps would be plus V squared plus E. Then we make an observation, V will always be less than V squared, and E will always be less than V squared. So let's get rid of both of them, and then we're just going to say the algorithm. Actually, the shortest path algorithm runs V squared. Okay, so what if the graph had orientation on it? Oh, I'm sorry. What if the graph had no cycles in it? So a directed acyclic graph, a graph with no cycles on it, that means you couldn't go to a node and then come back to the node. Could that make things any easier? So what we could do is, since you're starting at a node, when you go out in different directions, you'll know you'll never come back to any node you've ever visited before. What we could do is do a top-down sort, starting at the point you're at, and see all the places you can go to. And then run, again, the relax routine, but we're going to say for each vertex taken on at each step, we call the relax routine. So a topological or a top-down sort of the algorithm, we could use either the depth first search or the breadth first search. We would have all the paths from the first node to every other node, and we'd end up just calling relax for every path we hit along its way. So a topological sort, the first part takes order V plus E, whether you use depth first search or breadth first search. And then lines 3 through 5, which is really the relaxed part, even though it's driven by for loops. Lines 3 through 5 are executed on each vertex. And then for each vertex, the edge leaving the graph is examined exactly 1 time for each graph. So the number of times that would end up happening is V plus E also. So all we're really saying here is, if your graph, if the map that you're trying to run the shortest path algorithm on happens to have no cycles, you can't get from New York to Philadelphia and then back to New York. If for some reason that was the case, then instead of using a v squared algorithm, we could use a v plus e algorithm. And really, the only difference between this and Dijkstra's algorithm is the overriding algorithm in Dijkstra's is every time you pick a new city, you have to add it and then recheck, does that make all the other cities better? If the graph has no cycles, anytime you add a vertex, it only helps anything that came after. And that's where we get our savings from. Okay, and then another question would be, and this could be our last question, but it's an interesting question, is suppose you wanted to know, so Dijkstra's algorithm basically says, given a graph, and let's say an initial starting city, so let's say we were starting here, and we wanted to know how far away, what's the quickest way to get to all the other cities, starting from here. Okay, and also Dijkstra's algorithm requires that there are no negative edges. Because if there was a negative edge, then let's say the best way to get from here to here, forget about these numbers out here, the best way to get from here to here is some low number, but then you could take a negative edge and another negative edge, then you could actually, the distance could actually be a negative number when you're done. So Dijkstra's algorithm assumes that all the edges are positive numbers. So every time we say the best way to get from here to here, we look at this one with the smallest number and we're done. We don't want some negative edge coming in and giving a better answer. But suppose there was a concept of negative edges, and we want to figure out what's the best way to get to from one point to another. And suppose we wanted more information. Instead of saying, here's where we're starting, how far away are all the other points, why don't we find the answer to starting at every point, what is the best way to get to every other point? Okay, and include negative edges. So can you think of there wouldn't be a GPS question where there's negative edges. There'll never be like, the distance between New York and Boston is negative 50 miles. That'll never happen. But can you think of a question where to get from one place to another could be positive or negative? So it wouldn't be, it wouldn't be like maps or land or something like that. But there could be an example where, can you think of any? Okay, there could be investments, like let's say you invest money in something, you invest money in something and then later on you get payments back. So you lose money on one transaction and then positive money comes back and you want to see which is one where I end up with the most money. So a negative line could be you're making a payment and then the positive one is you get money back. So something like that's possible. So the way this algorithm, the way that this algorithm works is, it's the idea of Dijkstra's algorithm, but it can handle negative edges. Not only does it handle negative edges, it can also answer the question, what's the shortest path from every point to every other point? But it should take a longer time to run. Otherwise, we get rid of Dijkstra's algorithm. So anyway, the way it works is you record from each node. One thing I need to talk about. Suppose there was a negative cycle in the graph. In other words, suppose I can get from this point to this point to this point, back to this point, and the total is a negative number. And I'm trying to get to the smallest number possible, what could I then do to make it as small as possible? Keep going through the cycle forever, you'll run it off to negative infinity, right? So if there's ever a negative cycle, if that ever happened in an investment where, the amount of, well, I guess it would be, the amount of money you're getting is a negative number and the amount of money you're giving is positive, and you want to make the money you're losing as little as possible, you would just keep doing the 3 investments over and over until you became a billionaire, So one thing that this couldn't handle would be if there was a negative cycle, because you could just keep running the cycle over and over, make your number as more negative as possible. Okay, so the way this algorithm works is you take every vertex, and we're going to record in a 2-dimensional array how far it is from itself and how far it is from anything it can touch in one hop. So that's what this first matrix is. I hope this comes out on the camera. So every vertex is 0 away from itself. And, for example, vertex 1 in one hop. Well, let me talk about why this would be one hop. It is possible that the shortest path from one vertex to another, assuming you don't go through any cycles, would be how long? What's the longest number of hops in a shortest path? No, what's the most number of hops that a shortest path could have? So in other words, the shortest path from here to here could be one hop, or it could be 2 hops, or it could be 3 hops. But what's the most number of hops that the shortest path could have? Well, no, like 1, 2, 3, 4, 5, 6, 7, 8, 9, like 10. No, to get from here, from one point to another, without going through a cycle, what's the most number of hops it could possibly take?
5.
So it's V, the number of, well, it wouldn't hop to itself. Yeah. V minus 1. Worst case scenario, like maybe the best path is from here to here to here to here to here. But it would, so if you don't go through a cycle and you don't hop to yourself, you'd have to hit every other vertex except yourself. So that would be V minus 1. So the crux of this algorithm is, let's ask ourselves on one hop, what's the best way to get from every vertex to every other vertex? Once we have that answer, then say, okay, on 2 hops, and 3 hops, and 4 hops, and once we get to V minus 1 hops, we're done. So we make a matrix that says, how many hops would it, how long would it take for me to get from any vertex to any other vertex with at most 1 hop? So to get to yourself is 0, so the diagonals is 0. To get from vertex 1 to vertex 1 would take 0. To get from vertex 1 to vertex 2 takes 3. To get in 1 hop. To get from vertex 1 in 1 hop to vertex 3 is a cost of 8. To get from vertex 1 to vertex 4, there's an arrow pointing this way. You can't do it. So it takes infinity. And this is us handling negative numbers. To get from vertex 1 to vertex 5 takes negative 4. So we have negative 4. So we fill out this chart, and this chart will tell us the quickest way to get from every vertex to every other vertex by only taking 1 hop. Now, if you were to take this vertex and say, what would the answer be if I took 2 hops? At most 2 hops. So what we'd have to do is say, well, what if we were to get from one vertex that we can get to? If you can get to it, if it doesn't equal infinity, then see how long it takes to get from that one to your final destination. And once again, you're calling like the relax route, using the relax method. And this could handle negative numbers. Okay, so then after 2 passes, for 2 hops, for example, we could get from, so what changed on the first one? This one's 0, 3, 8. This infinity became a 2 to get from 1 to 4 using 2 hops. So we would go from 1 yeah, so we could go from to 5 with a cost of negative 4, and then from 5 to 4 with a cost of 6, so 6 and negative 4 is positive 2. So this became a 2 on the second pass. And so some of the numbers improved. So this infinity to go from 2 to 1, we can't go from 2 to 1 on 1 hop, but we can go from 2 to 1 by doing a 7 and a negative 4 for a total of 3. So this infinity became 3 on the second pass. So at each point, by adding an additional hop, you're going to keep doing this, and the numbers will get, hopefully some number will get smaller. And then any number that got smaller, you can say, would connecting through that one, it's kind of like a connecting flight, would connecting through there get me to my destination quicker? And if so, call it relax route. By the time we get to the distance matrix, and this is a 4 here, when this number becomes v minus 1, then nothing should ever improve. If we kept saying, can I connect from something else, nothing should ever improve. If something was improving, that means you have a negative cycle, and then you'll be improving it forever. But as long as your graph has no cycle in it, where the total of all the edges on the cycle is a negative number, then doing this more and more will not make anything better. You'll be stuck with these numbers. So a sketch of the algorithm is basically a sketch of this algorithm is basically this will be the code for it, and someone named Floyd gets credit for this algorithm. And basically we're going to take the algorithm, the labeling of the algorithms, convert it into a 2x2 distance matrix, how far every vertex is from itself. So one little side question. Suppose you had, you know how we say the two most common ways we like to represent a graph is either a matrix, a 2x2 matrix. If the edges don't have weights, we put zeros or ones. 1 means connected, 0 means not connected. And the other data structure we use is an array of linked lists. And depending on what our algorithm is, the data structure may make the algorithm run faster. But suppose you were given one of those representations and said convert it to the other one. So just, I don't know if I should draw that out, but if you were given an array of linked lists and said convert it into its equivalent matrix, how long would that take? What would be the run? What would you have to do? You'd have to create a matrix, a 2x2 matrix, put zeros everywhere. Then for every linked list, if you're connected to it, you have to update its number. So the first step, putting all the zeros in, would be v squared. The next step would be for every edge, change the number. So that would be e. So it would be v squared. So anytime you have an algorithm that has the graph represented one way, and then you have to do a step where it'd be better to represent it the other way, and you have to do this conversion, the conversion is going to be v squared. So don't bother doing that for an algorithm that runs quicker than v squared, but if you had some v cubed algorithm, and then converting it could make another step go quicker, then it might be worth it. Okay, but anyway, in this case, we're going to use a two-dimensional array. And the distances, the entries in the array are distance from each other, and we can allow negative numbers. And we're really going to do, this is kind of like the idea of the relaxed routine in Dijkstra's algorithm. We're going to say whatever the difference, whatever is the minimum, whatever is smaller out of going I to j, or going from I to k, where k is going to be number of hops. So in this case, I and j is going to end up being every combination from vertex to vertex, and the k, which is going to go 1, then 2, then 3, then 4. Yeah. I copied this out of our textbook. This should actually be b minus 1. Right? We don't have to do b hops. It should be b minus 1.
Well, it starts at 1 though, right? So if it would start at...
Well, yeah, so I guess if the vertices were from 0 to v,
yeah,
then 1 to v or 0 to v minus 1 would be the same thing. But I'm just thinking, the point I want to get across here is what we're taking the minimum of is from I to j, the best we know so far, or go from I to a number of hops, and then from that number of hops, you know, each time k goes up, there's a new thing we could get to a little bit better. And then, so we're basically constantly looking for better answers. Actually, letting it run an extra turn will let you know if you have a negative cycle, because if on the v time you run it, if you get a better answer, that means you're running through a negative cycle. Okay, so the algorithm that tells us, given a graph of vertices, what is the quickest way to get from every point to every other point? Not just from one point to wherever you're going. You're going from anywhere to anywhere. We can calculate that with an algorithm that runs v cubed. And this algorithm can handle negative edges. Dijkstra's can't handle negative edges. Because if there were negative edges, then one of the premises is every time we look at a node and say, what's the quickest way out, we take the smallest one and accept that as the answer. Taking the higher one, there might be a negative edge that gets us somewhere better, and then we can't use that assumption. So Dijkstra's algorithm runs v squared, tells you how to get from one point to all the other points, and can't handle negative edges. Floyd's algorithm can tell you the quickest way to get from any point to any other point, and can handle negative edges, as long as the graph doesn't have any negative cycle on it. And so that's kind of the world of searching algorithms, shortest path algorithms. So if you wanted to get from one point to all other points, and yet the graph had negative edges, what could we do? So we can't use Dijkstra's, can't handle negative edges. We could use this and just suffer the v cubed versus v squared, or maybe there's some algorithm in between.